We look at techniques of integration. There are a number of them, even though we are not going to look at all of them, but we will look at number one. We look at integration by parts. Then we will also look at trigonometric integration, then trigonometric substitution. After that, we will look at the method of partial fractions, and we'll end up by looking at improper integrals. So these techniques of this method of integration by parts is based on the product rule. So you will recall the product rule of differentiation, or for differentiation, where if you are finding the derivative ddx of u multiplied by v, we observed that we can fix u, then we find the derivative of v with respect to x, plus then we fix v, then we find the derivative of u with respect to x, like that. So after doing this, let us now introduce the integral sign, the integral operator. We integrate both sides with respect to x. So integrating both sides with respect to x, we get the following. On the left, in other words, what we are doing is we come with the integral sign. We have d dx here of uv, right? And since we are integrating with respect to x, we will put dx that side. This will be equal to the integral of u dv dx. We are integrating with respect to x, plus the integral of v du dx. We are integrating with respect to x. And you can see this and that gone, this and that gone, that and that gone. So we end up with the integral of u of duv on this side, which is equal to the integral of u dv plus the integral of v du, like that. And you will recall that if you have the integral of dx like that, then we said this is simply x. And we have this operator, we have this differential here. So, and we, by the fundamental theorem of integral calculus, we know that differentiation and integration kind of reverses each other. So in this case, you have the integral sign, you have this d, the operator d there, which tells you that you will have uv in this side, on this side, and then you have u dv there, plus the integral of v du. So making this subject to the formula, the integral of u dv is equal to uv minus the integral of v du. This is the formula that we are going to use. So how does this formula work? How does this formula work? Say, for instance, you are looking for the integral of, say, for argument's sake, x ln of x dx. Say, for argument's sake, it is like this. Then if you have this kind of a situation, then you will come and try to compare whatever is written here with that. So in other words, we must be able to choose which one should be our u and which one should be our dv, so that we can rewrite whatever is given as the formula on the right hand side there. So in this case, we will, as we are going to explain, we will choose this because we don't know how to integrate this. Then this will be our u. Then these two will be our dv. So our dv will be given by these two, x dx, and our u will just be the ln of x, because we know how to differentiate ln x, but we do not know how to integrate ln x. Okay, so that's what this brings us to some guidelines of choosing u, which for most of the problems that we are going to deal with will be very useful. Some guidelines for choosing u and dv. So if you happen to, let us write here, priorities for u. If you happen to find that as part of your integrand you have an inverse, it can be an inverse trigonometric function or an inverse hyperbolic function, then this will be the first candidate. The other ones will follow. So this is number one. Number two, if you happen to have ln x, then this will be your candidate for you. As we have done here, we see that we have ln x, therefore this ln x must be our u. It cannot be x dx. And then number three, if you happen to have x to the power of n, this is x to the power of 1. So this does not have a, it does not come before ln x. That is why this is our dv. And then number 4, if you have e to the kx, and then number 5, others, like both sine x and so on and so on. So in this case, our candidate for u will be ln x, and then our dv will be x dx. Maybe we should use this one as an example. So if we are to evaluate or integrate whatever, let us call it I, the integral of x, the ln of x dx. So we have said that we will let our u to be the ln of x, then the rest will be dv x dx. Remember, we are interested in the integral of u dv, which is equal to uv minus the integral of v du. So if we have this on the left hand side, we must find our u, and we have seen our u is this, and then whatever is remaining, this is our dv. So we have it like that. Du we differentiate, dv we integrate. So when we differentiate this, we'll be left with du equal to 1 over x dx. We integrate this side, v will be equal to x squared over 2. We don't have to write the c. So it tells us that now our I is equal to uv, u, and v. So it's x squared over 2, the ln of x, minus the integral of v du. V is this, so we can write our 1 over 2 there. Then we'll be left with x squared, this one, over x, that one, dx, like that. Like that, because this is du is 1 over x dx, v is x squared over 2. So we have x squared over 2, the ln of x, minus 1 over 2, the integral of x dx, which is going to give us x squared over 2, the ln of x, minus, then we know how to integrate x, so it's just x squared over 2. So we are left with x squared over 4 plus c. There we are. So that was example number 1. Example number 2, we can pick, say for argument's sake, the integral of arc sine of x dx. If we have the integral of arc sine of x dx, and we should never forget that we need the integral of u dv equal to uv minus the integral of v du, like that, right? So we come here. This is our left-hand side. We look at what we have here. So we must have our u. And according to our guidelines, inverse function have a priority to be called u. So in this case, we just have our u. Let us put an I there. Then let u be equal to the arc sine of x, because we know how to differentiate arc sine of x, but we do not know how to integrate it. That is why we are integrating that one here. So this is your u, and then your dv will be the remaining part. If we have taken this to be our u, we are only left with dx, isn't it? U is this part, dx is our dv, so dv is dx. Differentiate this side, you have du dx equal to 1 over 1 minus x squared with the square root. V is equal to x, like that. So our I, it's uv, is x, the arc sine of x, minus the integral of v du, which is x over the square root of 1 minus x squared dx, like that. All right. So, well, we may recall that if you have something like this, you can let, say, w equal to 1 minus x squared, so that dw will be equal to minus 2x dx, which tells us that minus 1 over 2 dw equal to x dx, isn't it? So in that case, we will have x, the arc sine of x. We have minus, this minus. Now we are bringing this. So we have got minus times minus, which will be plus. Then the integral of, 1 over 2, this, and then x dx, as we have noticed, it's minus 1 over 2 dw. So we will have our dw, and this is, let me write dw over the square root of w, like that, which of course is x, the arc sine of x, plus 1 over 2, the integral of w, the power minus 1 over 2 dw. And this is equal to x, the arc sine of x, plus 1 over 2. We find the integral, we add 1, we divide, then it will be half and a half cancel. So we have, in other words, we have w 1 over 2 over 1 over 2, say, plus c for that matter, and then half and half will cancel. We are left now with x, the arc sine of x, plus half and half is cancelled out. We are left with the square root of w, and w is 1 minus x squared plus our constant c. There we are. So that was our second example. We have already seen that if you have the natural logarithmic function, then you can do it the way we have done. So let us take the third example here. Third example, we look at, say, the integral, prefer to call it I here. I equal to x squared e to the exponent of x dx, like that. And then now we go back to our priorities for u, and then we observe that in this case we have got x to the power of n, x squared, e kx e to the power of x. So according to these priorities, we can see that we prefer this x to the power of n to be our u rather than that one. Okay. So if you are curious, you can swap them and see what will happen. So in this case, we will let u to be x squared. Then the remaining part dv will be e to the power of x dx, like that. U, we differentiate du equal to 2x dx. V, we integrate equal to e to the power of x, that beautiful function. So after doing this, we observe that our I is equal to uv x squared e to the power of x minus the integral of v du. We have 2x e to the power of x dx, like that. So for the second part, you can see that for this integral that we have here, we will need to let u again to be equal to x, our dv to be equal to e to the power of x dx. So du equal to dx and v equal to e to the power of x. So our I is equal to x squared e to the power of x minus our 2 there, open the bracket like this. Then we are interested in this. It's uv, which will be x e to the power of x minus the integral of v du, which will be e to the power of x dx, like that. And this is going to give us x squared e to the power of x minus 2 into x e to the power of x minus e to the power of x plus c. So we may leave it like that, or if we want, we may remove the brackets, or if we want, we may take e to the power of x out as a common factor, and so on and so on. Yeah, okay, I was saying that we may write x squared e to the power of x minus 2x e to the power of x plus 2e to the power of x plus c after removing the brackets. So you may have observed that in this example, we did the substitution twice. So we had a kind of repeated substitution. Okay, so for this kind of problems, there is another method which sometimes may be shorter. Yeah, it's shorter. Let me write here alternative method. Alternative method, which we call the Tipler method, something like that. Let us come back to what we have here. So you have your u, which is x squared, right? So we may say u, and it's because u we differentiate u and its derivatives. Then the other part will be dv and its integrals, or we integrate. So we have u, we have got dv this side, u this side, dv that side. What is our u? Our u, we said, is x squared. What is our dv? We said it's e to the power of x. We don't write dx, we can just write dx like that. Okay, so after that we differentiate this, we get 2x. We integrate this, we get e to the power of x. Differentiate that, you get 2. Integrate this, you get e to the power of x. Differentiate 2, get 0. Integrate, you get e to the power of x. Then we write them like this. This one goes with that. It's a plus. It's the first product, uv. All right, this is dv. So you have uv. And then this one will be negative. This one will be positive. Let me put positive like this. And then finally like that. So we read the solution like this. We are saying the integral of x squared e to the power of x dx is equal to uv. Okay, so we have x squared e to the power of x, go like that. Then we have a minus, put a minus sign here. Then we've got 2x, go like that, e to the power of x. Then this one is a plus, so plus 2 e to the power of x. Then this is 0, so it would have been, say minus here, it would have been minus the integral of 0 times e to the power of x dx. All right, but this is 0, so we end up with simply x squared e to the power of x minus 2x e to the power of x plus 2 e to the power of x plus c. Then if you look carefully, you will see that what we have here and that one, they look the same. So the method can be used to deal with repeated substitution. For example, let us take another one maybe which involves trigonometric function. Let me give here that tabular integration works very well when repeated substitutions are required. Then you may check this one. I will just do it using the tabular method. You can do it using the regular method. It can be done. Let us take an example here. We want to evaluate, I will call it I again, the integral of e to the power of 2x cosine of x dx, like that. Now, again, if you check your priorities for you, where did I put them? Where did I put the priorities for you? Here they are. We are saying priorities for you, inverse function, ln x, x to the power of n, e to the power of kx, others. So if we look at what we have, we can see e to the power of kx is that one. Cosine of x does not appear here, therefore it falls under others. So in this case, we must identify our u, we must identify our dv. So if we are using our tabular method, we will have our u, we will have our dv. What is our u in this case? From those priorities, u must be e to the power of 2x. Our dv must be cosine of x. We don't write dx here. We just identify them like that. Then this one we differentiate. The derivative of e to the power of 2x is e to the power of 2x times 2 according to chain rule. So it will be 2 e to the power of 2x. Integrate. The integral of cosine of x is sine of x. Differentiate, you get 4 e to the power of 2x. Integrate sine x, you get minus cosine of x. Now, maybe the question that may come to mind is, do we continue integrating and differentiating? Then immediately another question will rise, that when are we going to stop? Because we can see that this will never be zero. This will never be zero. So we can continue. Do we continue indefinitely? The answer is no. We don't just continue. We stop when we you can see here the integral. We have produced cosine of x again, a multiple of cosine of x. So the moment we get a constant multiple of whatever we started off with, we stop. Okay, so again, we will multiply them like this, multiply them like this, multiply them like that. This will be positive minus positive, like that. So how do we read the integral? Our I, let us call it I, this, it's equal to uv e to the power of 2x sine x. It's our uv minus this times that, but this one is already negative, so it will be a plus 2 e to the power of 2x cosine of x. Now, you see this one is coming diagonally. This one is horizontal. So we have minus, when you go horizontally, it will be our 4. Then we put the integral sign, our e to the power of 2x cosine of x dx, like that. Horizontally, we write it that way. It's this times that, that. All right. And then you can see that this is nothing else but 2x sine x plus 2e 2x cos x minus 4i, because this is exactly the same as what we started off with. So when we take 4i to the left-hand side, because we have got I here, it will be 5i. All right? It will be 5i equal to e to the power of 2x sine x plus 2e to the power of 2x cos x, like that. And then our I will be 1 over 5 into e to the power of 2x sine x plus 2e to the power of 2x cos x, like that, plus c. All right, so that settles it. That settles it. So the last example, maybe we can look at a situation where we have a definite integral. Let's say evaluate, I will call it I again. It's very convenient. Well, the integral from 0 to 1 of the arctan of x dx, like that. So in this case, no. Pardon me. Let us just call it the integral of arctan of x from 0 to 1 dx. And then for simplicity, to make our lives easier, we set I to be the integral of arctan of x dx. Observe that we didn't put the limits because we don't want to get confused. So we leave the limits, we call this I, and then we will let our u, according to our priorities, this is the inverse function, so our u will be arctan of x, then what is remaining is dv, like that. Differentiate, you get du equal to 1 over 1 plus x squared dx. Integrate, dv equal to dx here. So v equal to x, like that. So after doing that, it tells us that our I, it's uv, which is x arctan of x, uv, minus the integral of v dx, which is x over 1 plus x squared dx, like that. And this is going to be x arctan of x minus, you can do your, what do we call this? This is your u substitution, whatever. Or you can quickly observe that this can be written as the integral of, let me write here, x over 1 plus x squared dx, and we can put a 2 here and a 1 over 2 there, which it's evident if you let this to be your u, the derivative of 1 plus x squared will be 2x, there you are, and so on and so on. So we have got this, and this is x arctan of x minus 1 over 2, the ln of 1 plus x squared, like that. This is our I. Therefore, what we started off with, the integral from 0 to 1 arctan of x dx, will be equal to x arctan of x. You can do it here, or you say minus 1 over 2, the ln 1 plus x squared, and then our limits from 0 to 1. So in this case, we substitute 1 here, the arctan of 1, minus 1 over 2, the ln of, you put 1 here, it will be the ln of 2, minus, if you put 0 here, this will be 0, you put 0 here, this will be the ln of 1, which is 0, so you are subtracting 0. And then you take your calculator, put it in a radian mode. Mine, it's in R there, maybe you can see it, I don't know, but it's in radian mode. So we just, because the calculator is already in radian mode, we can see that arctan of 1, let me just evaluate this, is pi over 4. So we have pi over 4 minus 1 over 2, the ln of 2, or ln of square root of 2 if we prefer. So that is the case, which is approximately, okay, let us subtract the ln of square root of 2, close the brackets. We have approximately 0.439. This is preferable. So you may look at the examples or exercises in your pamphlet, and also the examples which are done in your pamphlet, because when you are preparing for the test or the exam, you should never ignore examples. You may find them there.